Welcome back. Today we're going to talk about Gaussian elimination, which is the main technique for solving systems of linear equations in the simplest so-called regular case. So here's a very simple example of a pair of linear equations, and as you all know, if you take this equation and multiply it by 2 and add it to the second equation, when you do that you get 2x plus 2y is equal to 4. And when you add them, you get the new equation 4y is equal to 4, which of course has the solution y is equal to 1. And when you plug y is equal to 1 into the first equation, you conclude that x is equal to 1. Now, we're going to convert this into a matrix equation and use a sort of algorithm or sort of more mechanical way to solve these kinds of equations. So the first thing that you do is to make a matrix equation is you look at the coefficients of the equation on the left-hand side and you put those in a matrix. So the matrix is 1, 1, minus 2, 2. And you write the equation this times xy is equal to 2, 0. Okay. Now, I suggest you pause right here and just confirm for yourself that this equation right here, this single matrix equation, is exactly the same thing as the original two equations. If you write out this matrix multiplication, you get two equations which are exactly the original ones. Okay, now in terms of matrices, here's the main point, and it's really a very simple one, which is that the operation of multiplying the first equation and adding it to the second, in terms of matrices, is just the same thing in terms of the rows of the matrix. You multiply this row, the row of this matrix times 2 and add to the second one. And you have to do the same thing to both sides. You multiply this by 2 and add it to the second one. And when you do that, you get a new matrix equation. The first row doesn't change because you haven't done anything to that. The second row becomes 0, 4. Excuse me, I shouldn't have written this 0 here. This becomes a 4. Okay, now this matrix equation, the first one, is exactly equivalent to the second equation. And the second equation has a particularly nice form. So I'll put a box around it. And this matrix here is upper triangular. That just means that all of the entries below the diagonal are 0. And it's very easy to solve such an equation because you start from the last row and work your way up. The last row says 4y is equal to 2. So, excuse me, 4. So that says that y is equal to 1. And then we just went back up to the next row. And since we already knew y, we plug in y to get, plug in y is equal to 1 to get x is equal to 1. And that process is what's called back substitution. Okay, and Gaussian elimination is basically just trying to put any matrix into this form and then solving it by back substitution. Okay, so let's look at what we just did in terms of equations, what that becomes when we think of it in terms of matrices. So here's the main point. So I'll write down a general 2 by 2 matrix, A, B, C, D. And suppose you wanted to multiply the first row by 2 and add it to the second, this thing we've been doing all the time. Well, here's the fact. that's exactly the same thing as multiplying on the left by this 2 by 2 matrix. Because if you do this matrix multiplication out, what you get is A, B, 2A plus C, 2B plus D, which is indeed 2 times the first row added to the second. So this is the first big point of Gaussian elimination. The fact is that doing these row operations which we've been doing, adding a multiple of one row to a second, correspond in terms of matrices to multiplying matrices on the left. So we're going to think of solving a system of equations by doing a bunch of operations where we multiply by matrices on the left. Okay, so let's go back and solve that simple equation that we had before, thinking of it in these terms. So this is this 2 by 2 equation we solved a few moments ago. And in the language that we're talking about, we're going to multiply on the left by the matrix 1, 0, 2, 1. And in order to keep things legitimate, you have to multiply both sides on the left by the same thing. And after you do that, you have this equation 1, 1, 0, 4 is equal to 2, 4. And that's our upper triangular equation, which we know how to solve. So let's do a 3-variable example. So the first thing to do is to convert this into a matrix equation, which is easy enough. 1, 1, 1, 1, 2, minus 1, 2, minus 1, 1. That's the coefficients on the left. That times x, y, z is equal to 4, 4, 1. Okay, now I'm going to simplify this even a little bit further, and I'm going to write both all of the coefficients as follows. 1, 1, 1, 1, 2, minus 1, 2, minus 1, 1. That was the left-hand side, and then you draw a line and you draw the right-hand side. This is sometimes called the augmented matrix. And this has all of the information about the system of equations in it. On the left-hand side of this bar are the coefficients of the variables, and on the right-hand side is the right-hand side of the equation, and the x's and y's and z's are all gone. Okay, so what we're going to do is perform a series of row operations to this augmented matrix to put it into triangular form. And by putting this into an augmented matrix, when I do a row operation to this part of the matrix, I'll do the same row operation to this part of the matrix. And that's what I was saying before about doing the same operation on both sides. So let's see how that works. So the first step is let's get rid of this one, and where we're going to do that is we're going to multiply the first row by minus 1 and add it. I get this matrix. And let's do that again. Let's get rid of this 2 by multiplying the first row by minus 2 and adding it to the third row. And I'll indicate what happens when you do that up here. And what you get is this matrix indicated here. Okay, so what we've done is we've so to speak, killed off these two coefficients. We're trying to make the matrix upper triangular, so the only thing left to do is to get rid of this one. And the way I'm going to do that is I'm going to do the row operation where I multiply this row by 3 and add the 2. And what happens when I do that is I get the following matrix. Okay, so now the matrix is in upper triangular form, and it's very easy to solve it by back substitution. The third row tells you that Z is equal to 1. And then when you plug that into the second row, you get Y minus 2 is equal to 0, which says that Y is equal to 2. And when you plug both of those in for the first row, you get that X plus 2 plus 1 is equal to 4, which says that X is equal to 1. Okay, this slide has just the names of some different types of matrices which play a role in what we just did. An elementary matrix is one which has ones on the diagonal. It has a single non-entry term below the diagonal and is 0 everywhere above the diagonal. This corresponds, when you multiply by something like this on the left, to adding k times one row to another row, and which rows depend on the position of this k. And a lower triangular matrix is simply one where all of the entries above the diagonal are 0. And a special lower triangular matrix is one where not only is it 0 above the diagonal, but the entries on the diagonal are all 1. And finally, an upper triangular matrix is one which only lives above the diagonal. So now let's suppose we have a general matrix equation with n equations and n unknowns. So here A is an n by n matrix. And I'll write the equation as A times this vector is equal to this vector of constants. And I'm leaving a space here because I'm going to be putting some other stuff in there. And what we just saw, the technique of Gaussian elimination that we just saw, amounted to the following thing. What I want to do is I want to multiply both sides of this equation by some elementary matrix, E1, which kills off one of the lower triangular terms, one of the terms below the diagonal of A. That's what multiplying on the left by elementary matrices enables you to do. And then you do it again, and you do this repeatedly, and after a while, after you've done this some number of times, if you're lucky, what you've done is this product, ER times E1 times A, this matrix product is supposed to be upper triangular. U is I've written U because it's intended to be, remind you that this is upper triangular. And this product of matrices here, it's a product of elementary matrices, and I mentioned before that such a thing is a lower triangular matrix. So what I've done is I've essentially done the following computation. I've found L such that L times A is equal to U, where L is special, lower triangular, and U is upper triangular. Okay, so if I have A as the coefficient matrix of a system of equations, and I can multiply it on the left by a special lower triangular matrix, L, such that the result is upper triangular, then I can solve it simply because any equation with U, you can easily solve by back substitution. And what's going on the other side hardly matters. You just carry these along for the ride and apply them to the constants that appear on the other side. So here's a summary of what we just did. Suppose I had a matrix equation like this. Now I've introduced a little new shorthand. X stands for, with an arrow over it, stands for this column vector x1 through xn, and C stands for this column vector c1 through cn. So this right here is a more or less general matrix equation with n equations and n unknowns. And what I was hoping is that I can find a lower triangular matrix L, so that if I multiply both sides of this equation, I can put it into this form, where now this U is upper triangular, and this is an equation that's easy to solve. So the question is, when is this possible? If you take any matrix A, can you multiply it on the left and make it upper triangular? So I'll state that as a question, which is if you take any A, can you find L such that LA is U, which is upper triangular? So this L, of course, is lower triangular. So why don't you pause the presentation for a moment and think about that. Maybe do a few examples and see if you can find a matrix L for any such A. And if not, which A's can you do this way? Okay, so, well, I'm not going to really answer the question. Definition. A is regular if this works. That is, if you can find L lower triangular, special lower triangular, such that LA is upper triangular. So this is just the definition of the word regular, and it's a non-answer to the question. I'm just calling the matrices which answer the question regular. Now, implicit in having a name for such a thing is that not every matrix is regular, and we'll talk about that a little bit more, but for now, let's just accept this as the definition, and we say a system of equations is regular if the matrix is regular. A system of linear equations given by matrix A. And we have an algorithm for solving any such, any regular equation. And that's what this word regular case refers to in the title of the section. Now, I need to point out something which might be just a little bit confusing at first, but the book states things slightly differently. So what the book says, I'll call this definition prime, is that A is regular if I can find L and U, lower triangular, special lower triangular, and upper triangular as usual, such that LU is equal to A. I'll put a box around this. Okay, one last final bit of terminology. Suppose you have a matrix A and you write it as LU, where again L is special lower triangular and U is upper triangular. This is called, strangely enough, the LU decomposition. Of A. And for such a decomposition exists exactly if A is regular. Now, the connection between writing A is equal to LU and writing LA is equal to U. This is what I'm talking about right here in the LU decomposition. This is what came up in practice when we were solving systems of equations. Well, the relationship between these two things is very simple. It's moving L inverse. It's multiplying by L inverse. But that doesn't come till the next section, so let's not worry about that for now. And I'm just going to do one last example to illustrate how you solve an equation by using this decomposition. Okay, so let's look at this example of a system of three equations and solve it by the algorithm we just discussed. So that means I want to look at this matrix and reduce it to an upper triangular matrix by a series of row operations, which means multiplying it on the left by elementary matrices. And what I'm going to do is I'm going to first multiply it by the elementary matrix amounting to this minus 2, and then another elementary matrix which is going to kill this 3. And the last step isn't that easy to see. You have to work out the intermediate steps, but it turns out the last step is going to involve adding 1 times the second row to the third. So that gives 3 elementary matrices with a minus 2, a minus 3, and a 1 in them. And when you take the product of those 3 elementary matrices, you get an elementary matrix L as follows. You get this matrix identity, where now this is L, and this is A, and this is U. And in order to finish solving the equation, we take this matrix L and multiply it by this vector V, this vector 2, 5, 3, to get the following. This is what you get. So this is the matrix U. And 2, 1, 2 is what you get when you multiply this matrix L times this on the other side. And so we've therefore replaced the original equation with an equivalent equation, which is upper triangular and very easy to solve. And I'll just finish by writing down the solution. You look at the last row and you immediately conclude that Z is equal to 1. And if you plug, Z is equal to minus 1. And if you plug minus 1 into the second row, you conclude that Y is equal to 1. And then finally going back and looking at the first row, you conclude that X is equal to 2. Okay, so let's look at this example of a system of three equations and solve it by the algorithm we just discussed. So that means I want to look at this matrix and reduce it to an upper triangular matrix by a series of row operations, which means multiplying it on the left by elementary matrices. And what I'm going to do is I'm going to first multiply it by the elementary matrix amounting to this minus 2, and then another elementary matrix which is going to kill this 3. And the last step isn't that easy to see. You have to work out the intermediate steps, but it turns out the last step is going to involve adding 1 times the second row to the third. So that gives 3 elementary matrices with a minus 2, a minus 3, and a 1 in them. And when you take the product of those 3 elementary matrices, you get an elementary matrix L as follows. You get this matrix identity, where now this is L, and this is A, and this is U. And in order to finish solving the equation, we take this matrix L and multiply it by this vector V, this vector 2, 5, 3, to get the following. This is what you get. So this is the matrix U, and 2, 1, 2 is what you get when you multiply this matrix L times this on the other side. And so we've therefore replaced the original equation with an equivalent equation, which is upper triangular and very easy to solve. And I'll just finish by writing down the solution. You look at the last row and you immediately conclude that Z is equal to 1. And if you plug, Z is equal to minus 1. And if you plug minus 1 into the second row, you conclude that Y is equal to 1. And then finally going back and looking at the first row, you conclude that X is equal to 2.